Hello, my name is Andrew Abraham. I'm with Lehigh University in the Department of Mechanical Engineering. And Lehigh has teamed up with Penn State to work on the Lunar project. Specifically, Lehigh's role is Guidance, Navigation, and Control, or GNC. And what we have done is constructed a Hopper spacecraft simulator, which is what you see in front of you. Now, this Hopper spacecraft simulator has the goal of testing out our guidance, navigation, and control algorithms. The same algorithms that we want to put on board the Lunar spacecraft. So this simulator is mounted on our 1 degree of freedom test stand, which is this wooden structure that you see surrounding the spacecraft simulator. It's free to rotate about a single axis. And so what we're trying to do is develop algorithms which can adequately control the attitude of the spacecraft. So as you can see, it's quite unstable. And so hopefully our control algorithms will stabilize the platform that you see here. Now let me talk a little bit about this spacecraft simulator. The frame is octagonal in shape. We have an inner frame and an outer frame. We also have some landing gear and some landing pads. The spacecraft simulator is powered by 4 very large lithium polymer batteries, which are located in the center of the spacecraft. Thrust is produced by these 4 very large ducted fans. Now each ducted fan can produce about 10 pounds of thrust, which is a total of 40 pounds, obviously. Now in the real spacecraft, we would not have ducted fans because obviously there's no air on the moon. So instead of these ducted fans, we would have small rocket motors. Okay? But the principle is essentially the same. We're producing thrust, and we have to control that thrust. So if the camera would pan in a little bit, I would just like to point out a couple of important devices on this spacecraft simulator. This device right here is our IMU, which stands for Inertial Measurement Unit. And the IMU can sense accelerations and can sense rate of rotations about 3 independent axes. And with that information, we can actually determine the attitude of the spacecraft, or the direction that it's pointing. Okay? So, with that information, we feed that attitude information into this control computer, which you see right here is this structure with a large amount of wires attached to it. That computer is an Arduino control board, a microcontroller, and we have programmed some guidance and navigation algorithms in there. Some simple PD controls right now. We'll work our way up to PID controls and then more advanced controls from there. But the basic idea is that the first thing we want to do is have this Hopper control itself and be very horizontal. We don't want it to roll over unexpectedly. And so the way we do that is we control the amount of thrust on this engine and on this engine. So if the IMU detects the attitude of the spacecraft to be in this configuration where it's pitched down a little bit, the computer will command this engine to increase thrust and this one to decrease thrust, thereby creating a torque and restoring the Hopper spacecraft simulator to horizontal and level flight.
Hi, my name is Evan Mukasey, and I'm also part of the Department of Mechanical Engineering here at Lehigh University. And I'd like to talk a little bit about these motors specifically. So, in order to control this spacecraft, we have to know precisely how these motors perform. And in order to do that, what we have built is a motor test stand. And so the point of this is to mount one of these motors on the test stand and give it an input signal from our computer. And using some software that we have on the computer, we can take that input signal and transfer that to an output based on how the motor performs. And what we need to know is thrust. Specifically, we need to know static thrust and dynamic thrust. So once we have that information, we can then tell our computer how precisely to control these motors. So when we have a degree of tilt here, we know exactly how much thrust we need to bring that to level. So if you follow me over here, you can see some additional hardware that we're using here for testing. And this is our joystick. What we use this for is to provide that computer with a reference signal in the control loop. So if we're hovering level and we tilt this joystick all the way to the left, we tell the computer that we want it to do whatever it has to do to tilt to a certain degree to the left, however we code it. And the same goes to the right and all the other axes. And this here is our throttle control. This tells the computer where we want our throttle. We can push that up and down to control that.
So now Evan will do a flight test, and this test will be on the 1 degree of freedom test stand. And so the computer is telling the hopper to go back to the correct orientation after Evan disturbs it with his hand. Let's get a closer shot. Disturb it. Disturb it. Here, just, no, pick it back up and give it a whack with your hand. So each one of these ducted fans produces 10 pounds of thrust. And what I want to do is just give you an idea of what that thrust kind of feels like. So here I have just a regular piece of paper. And what I'm going to do is I'm going to stick this piece of paper underneath the ducted fan. And it'll only be going at about maybe around 20-25% capacity. Okay? Quite by accident, we've actually shredded part of our paper with only the force of the exhaust wind. Thank you.